Okay, so the last video we talked about some definitions of trees, and we have this little drawing of a tree with root, and the pointer to the root points to 3, which then points to a 5 and the 7. We could draw the little arrowheads there, but not, I usually leave them out. And so we're going to start talking about how we can represent a tree in Java, and also some, how we can actually arrange the data in a sensible way. So to start with, think about the linked list. When we made our linked list, the linked list was kind of similar. So a linked list, we had nodes, and we had, A, B, C, and we had a pointer maybe to the front of the linked list. And that was, that was all pretty easy to do, and it just worked. And we made a class for node, and then we made a class for linked list that had a node. And we're going to do something similar for a binary tree. So before we do that, I want you to think about it a little bit and see if you can come up with a diagram for a basically for what your internal representation of tree will be like. And it could be a UML diagram, it could be just some notes on it, but pause this video for a minute and just try to draw something out. And remember, we're talking about a binary tree, so every child, every node, so like here we'll have this node here as the root, and it can have 2 children, but a node can have 0 children, like this. Well, let's say this 7 has 0, and this 5 might only have a right child, which maybe has a value of, I don't know, 6 in it, let's say. So you can have 0, 1, or 2 children, and we typically refer to them as left and right. So pause the video and see what you come up with. Okay, so welcome back. And you might have come up with a number of things. So this is probably how I would think of it, is that I'm going to have this thing called a node. And the node, I'll move this up, the node is going to have 3 components. It's going to have the data, and that would be a pointer to a string, so, or maybe to an int, so it would actually hold the value. We'll just make them ints for our purposes now. And then we're also going to have a left and a right pointer. And those are going to point to the respected left and right. And when I actually draw these, I just draw the circles usually, but that's kind of what's going on. I'm going to have this class that has those 3 pieces of information, and then I'll have another class called tree, and I'm actually going to call it a binary tree, or I'll call it BS tree, and not because it's full of BS, but the BS stands for something that we're going to define in a little bit. And that tree, amongst other things, is going to have a root in it, and the root is going to refer to that first node, or be null in the case of nothing there. All right, so that's kind of the idea, and let's actually put this in. All right, so now let's code this up. So let's see, let's find the directory here. I'll copy these all into, by the time you see this, I think I'm going to have to make a new folder. Oh, no, I don't want to put it in the summer. I want to put it in staging, because this is where I'm testing and writing everything. And we'll call this a tree node, because that way we can have it in the same thing as our regular node. So, our usual stuff. And I don't know if I actually need these for what we're writing, probably not. But so we'll have our public class tree node, and we're going to have our private data, and we'll just make that an int for the time being, just like we did with the linked list. Remember, in reality, this is going to be stuff. It might be, a company, so it'll be human resource records with name and social security number and salary and all that. Or it might be like a research project where you have a tree of data items because you're cataloging plants, and so it's the name of the plant and various measurements on it. But we're just going to put int in it for now. And we're also going to have left and right pointers. And we're going to make our constructor. So our constructor, we're going to have our public tree node. And this will be our first constructor. And it'll just be data equals 0, left equals null, right equals null. And I'm just going to stop at that and Java see it just to make sure we're good. And then we'll have another constructor. And this one will get int data. And we'll say this dot data equals data. And left equals null, right equals null. And for this one, what we'll do is we'll now change it. So it will call this with 0 in it. We're going to probably want to put in a semicolon over here. Okay, so that's our basics. We're also going to want to get getters and setters for this. I don't know if I have this set up or not. Okay, so it's not doing it for me. I'm going to have to type them all in. So we're going to do that now. And I'm not going to make you sit through me writing all of this here. What I'm going to do is I'm going to stop this video, write all the getters and setters and also the rest of the basic classes for this. And then we're going to be ready to proceed. Okay, so I finished putting in the rest of the tree nodes into it. Not the tree nodes, but the rest of the class. So again, we have these two constructors, and notice I'm not bothering with a constructor with left and right. You might want to put a constructor in with both the left and the right pointers, but usually, as you'll see, we just want our left and right to be null, and then we'll set them later on. And so here we have our set data, our set left, our set right, so we can now manipulate our nodes. And we also have our get data, our get left, and our get right. So this is as complete as we want for now, and we could, of course, compile this. Well, that's the driver, but which I already wrote, but Java's the tree node. And let's look at, well, we'll look at the driver for a second, because then the heart of this, of what we're going to do in this unit, is we're going to look at the tree class itself, and we just make a new tree here. You know, nothing earth-shattering. And so let's look at the BS tree. And again, I haven't decided what the BS is for, and I know you may feel that I'm full of it, but it will become clear soon. So here is our BS tree, and notice we start with a constructor, and basically our constructor is going to just make the root going to be null. And so what we then have is I then have this little thing called seed, and this is kind of manually building the tree. And so what I'd like you to do, this actual code is going to be under the day-to-day for today, day 14, under part 1. And you'll see, I have it under staging, but I'll copy this over to the summer 2020 day-to-day 14 part 1, and you will see these files, and this code here for seed is going to be in that. And what I'd like you to do is pause the video again and then just step through it and draw the diagram of the tree that this will create. All right? So pause now and take a few minutes, and again, just draw the circles with the arrows just like you're doing it manually. Okay, so take a few minutes, pause this, and then unpause it once you're done. Okay, so welcome back. And what we're going to look at here is we're going to go through this manually. And so here, make the font, I hope the font is big enough. We're going to start with a tree node T, and we're going to make a new node which has a 10 in it. So that's going to have a 10. And its left and its right are null, so I'm not going to draw anything there. And then in our second line over here, we're going to say root points to it. So now root points to that node. Then we're going to make a new node, T points to, that T is going to be a new node which has a data of 5. So right now, t is pointing to this. And then we're going to say root set its left to t. And then, and notice that I'm using my fancy new drawing tablet stylus thing, much like R2D2. But I've got these high-res graphics, you know, like this going on here. So I think you should, you know, appreciate the awesome tech we got going on here. And so now we're going to make a new t is going to now be assigned to a new node, and we could erase this, which I guess I will. And then we make one. So now t is going to have a new node which has a 20 in it. So that'll be t. And then we're going to point roots right to it. And so notice we're building out our t. So now we got a little bit trickier here. So roots get left, its set right is going to be set to a new tree node with 8 in it. Then we'll make another node with t, so I'll just cross that out, and t will be a new node which has a 15, and that's going to be going to roots get right, set left. So we're going to have a 15 over here. And then finally, I think finally, we're going to say t equals new tree node of 22, and that's going to be roots get right. So that's root get right, set right of 22. And that is our binary tree. So that was pretty much that, and it was pretty straightforward to put through. And let's look at this tree for a second. This tree is kind of, it's a binary tree, and we know that because every node has 0, like, you know, the node 8 has a 0 in it, you know, 0 children. 0 children, 0 children, 1 child, like the 5 has 1 child, and then the 20 and the 10 nodes all have 2 children. So this is a binary tree. But this is a special type of binary tree because there's a particular ordering to the nodes. So again, pause the video for a second and look at this and see if you can think about the relationship between the values in the nodes. Okay, so if you thought about it, hopefully you saw that the value in any given node is less than, or if you look at any node, if you look at the 10, every node on the left, so the 5 and the 8, is less than 10. And every node on the right, the 20, the 15, and the 22, are greater than the 10. So then if we go down to the 5, so at the next level here, there's no nodes to the left, but the 8 is greater. If we look at the 20, 15 on its left is less, 22 on its right is greater. So what we're seeing is in this tree, every node, given any node, every node in its left subtree has a lower value, a lesser value, and every node in its right subtree has a greater value. That's known as a binary search tree. And that's a, so BST, binary search tree, or BS tree, binary search tree. And that's a tree with a special type of property. It's got an ordering to it. And that ordering, you know, that lets us exploit certain features to it. All right, so what we're going to do next is we're going to do some operations on the binary search tree. So the total operations we're going to do is we're going to want to be able to, you know, search for stuff in a binary search tree. And presumably this will be kind of efficient to do because it's a binary search tree, you know, and so why would you call it that otherwise? We're also going to have to insert and delete items to and from this tree. We're going to have to add things into it and remove things from it. And we're also going to want to do what's known as traverse the tree, or we'll say print the tree, like get all of the data in the tree. And we're going to do all of that over the next series of steps. All right, so I'm going to pause the video now, like literally click on the stop recording button so that I can set things up for part 2 of this, where we are going to talk about inserting into a binary search tree and then writing the code for that. Okay, so normally when we do write our code, normally the first thing we write is going to be our insert routine, but we're not going to do that this time because we've got this seed routine here, which which I put in for you, which you trace through to create that tree that you see up on your screen. And if we look at our binary search tree here, our seed routine just manually builds the tree. So we're actually going to first write the search routine. And so for the search routine, let's think about this. This is where we can exploit the binary search-ness of this. So like if we had a linked list, if we had a list with these elements in it, with no ordering, we'd have something like, I don't know, maybe, I'll put it up here, 10, then we'd have, then 10 to 5 to, 20 to 8 to, et cetera, to 15 to 22. And so we just have to start at the front and go next, 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 next until we got all the way, to the 22, or we didn't find it. And this would be, this would be a linear operation, and it would just kind of be blindly going through, and we've done that before. But with the binary search tree, we can do better. If we start at the root, like let's suppose we're looking for the 10. Well, if we're looking for the 10, we got it. But let's suppose we're looking for the 15. So if the key we're looking for is 15, we start at the 10, and then we're like, well, is it the 10? No. Well, where should we look? We either have to look at the left or the right, or I guess we could look at both, but we don't want to look at both. But remember, in the binary search tree, all the values on the left subtree are less and all on the right are greater. So if we're looking for, let's say, the 15, 15 is greater than 10, so we move over to here. We move over to this 20. Now that's not it, but 15 is less than the 20, and so we come over here to the 15, and wow, we've got it. So at each stage, we can make a decision. Do we look on the left side of the tree, or do we look on the right side of the tree? And that's really the key. And think about what algorithm does this seem similar to in terms of searching. Now for implementation, and that's what we're going to talk about, or that's what we are going to do next, is we're going to fill in some of this search routine. And let's think about this for a second. As we're going to be either going left or right. And what we're going to do is, like, let's say we're not looking for the 15. Let's say we're looking for a 17. So it's not the 10, so we go right. It's not the 20, so we go left. It's not the 15, so we go right. And then we've fallen off the tree. And that's when we know it's not there. So let's put in a framework for this. So instead of just returning the -1, and we're just returning the value in the tree, and we'll throw an exception if it isn't found. So we've got to keep doing this until we're found. So well, actually, let's start with a temporary node, and we'll call it current, tree node current, and we'll start that at the root, because we never want to move the root, just like we don't want to move the front of a linked list. And we want to keep doing something, so we're going to have a while loop. And so what you want to figure out is what goes here. When do you want to stop? And then we've got some decisions to make. So if you remember, when we were looking at our tree, there were 3 possibilities. One is if what we're looking for is less, one is if what we're looking for is greater, and one is if what we're looking for is what we're looking for. So those are our 3 cases. So we can have if the currents get value, well, why don't we actually factor that out? Current value equals current get value. So if current value equals our key, we're going to do something. Otherwise, if current value is less than our key, we're going to do something else. But if it's not equal to the key, and if it's not less than the key, we're going to do yet another thing. And what you're going to do, and then finally, if we get through this loop, do we really want to return -1, or do we want to do something else? All right, and so that's going to be your task. And over here in the driver, and this is all under the part 2 search folder for the under day 14. What your job is to finish this routine. And in the driver, you'll notice we have a commented out section where we call search on 10, 15, and 17. And notice that I am doing a null pointer exception here, so you'll have to finish that up in the code. So your task is to finish this search routine and test it thoroughly, and also give some thought as to what's the runtime for this, how efficient is this, and we're going to come back to that a little bit later. So we're going to stop the video here, we're going to pause the video here, and when we continue the video, or rather unpause the video, when you've got your working search routine. And then the next thing we're going to do is we're going to write our insert routine. Okay, so let's take a look at that search routine that you just finished out. And so for search, we just had to fill in the last few pieces. So the first thing is we're going to start the current node at the root. And while that's not null, because once that's null, nothing's there. Well, if your tree also, it's worth noting, if your tree starts at null, if it's empty, you clearly can't find anything in there. Now, so then we enter our loop, and we outlined that we had a while loop before that we paused. And while we're not null, we just have to look for the value. And so here we get our current value. We didn't have to do this. We could have just we could have gotten the current. We could have just done the get data each time through. And apologies, I know I wrote get value in the last or in an earlier video, earlier before. I'm actually making these as separate videos and I'm putting them all together, and it should have been get data. But if we found it, if we found the key in question, we'd return it. We would return, and really we don't want to return the key, we really want to return current.get value, which is just current value. Because remember, this is not going to be just an int. This is just for demo purposes. It's just for us building the data structure. In reality, this is going to be a whole bunch of information. It's going to be, names, information, like it might be, like this might be a tree that you're using to store users for your, users of your site, and their account information, or a shopping cart, or might be a research project that you're doing research on, like some plants, and you should have the name and all sorts of stuff. But anyway, if not, we have to just move down the tree, and it's analogous to the linked list where we do get next, but we have to make a decision. So for example, if we're looking for the 20, we come in and we start with current value at 10, and since the key we're looking for is 20 is greater than the current value, or the current value is less than the key, we move current to get right. So now it's at the 20. And then the next time through the loop, it's equal, so we return it. And if we're looking for something that isn't there, like a 17, it'll start at the 10, go to the right, and then 20 is bigger than the 17, so we come to the left at the 15. We're then looking for something that's bigger than the 15, so we go to the right, we end up at null, and we exit the loop. And at the end, we're just going to throw a null pointer exception. There's probably a better exception to deal with on this. Or we might even just want to return, well, we can't return null because right now we're returning an int. But if we were returning like a class with a person or something, we then could return null. So maybe there are better ways for that return, but this still illustrates the basic algorithm. And in the driver, we just have those calls. So we look for 10, we look for 15, and then we look for 17. And since we know 17 isn't there, it's going to throw that exception. And let's see what it looks like. So driver, I just want to make sure everything is compiled. And boom, there we have it. So that is our search. And, again, pretty straightforward. But now we can move to our next thing, which is insertion. We want to add something to our tree. Now, adding something to our tree, if we look over here, if we look at the document, and let's just, if we add something to our tree, we can't just put it anywhere. All right, we just can't say like, oh, I want to add a I do want to add a 17. I'm just going to put it right over here. You can't do that. You've got to do it so that you fulfill the binary search tree property. The idea that everything on the left is less, everything on the left subtree is less than the given node, and everything on the right subtree is bigger than a given node. So let's suppose we want to insert a 17. So let's see where we can insert it. So pause the video for a minute and see if you can figure out where you should insert this to make it a legal binary search tree. Okay, so as you see, you could insert a 17. Well, the 17, it can't go here. It's less than the 20. It could go here. You could insert the 17 between the 15 and the 20, but you can also insert the 17 down here underneath the 15. So whenever you're doing an insertion, a lot of the time you can insert in multiple locations. There's more than one location. Frequently there are two locations where you can insert. So think about what's easier. If we put the 17 over here, well, then we're going to have to point the 17 at the 15, point the 20 at the 17. We're going to have to move a couple things around. But if we put the 17 down here, we don't really have to do anything. We just have to get a pointer to this 15 and then throw the 17 down here. And it turns out that we can always do this. When we're doing an insertion, we always insert as a new leaf. Always insert as a new leaf. All right, that makes your life much easier because then it's fewer pointers to rearrange. And you can always do that. So let's think about this algorithmically a little bit. If we want to do our insert and we want to insert a 17, we're going to make a new node which points to the 17. And then we have to get to a situation where we can put the 17 in here. So we got to find where the 17 goes. And, you know, conveniently enough, we just wrote a search routine. If we were to search for a 17, we'd start here at the 10, come down to the 20, over to the 15, and then over to the 17. So we can actually use the same logic as our search routine to do this, but there's a problem. If we search for the 17 and we get all the way over to here, if we get a node, a pointer over to here, we no longer have the pointer to the 15. We need a pointer to before where we insert. If we're inserting a 17 down here, we need to get a pointer over to this location. We can't go all the way to null. And so we're going to talk about how we do that algorithmically now. So let's start with our code. And this is our search routine, and if we'll get back up to it. And the routine in question is going to be very similar. So what I'm actually going to do is I'm actually going to copy this and make a few changes. This is going to be insert. And the first thing we're going to do is we're going to use a technique that I really like for working with pointers, and I use this for linked lists too. I call it piggybacking. I don't know if that's an official term or not, but I always call it that. And so the idea is, while we are searching for this location where the 17 is going to go, we're going to piggyback a second pointer so that if our pointer goes to the 20, the piggyback is going to be over here. The trailer is going to be here. Then it's going to catch up to this one, and the front is going to go over to here. And so we're going to have a pointer. The trailer is going to catch up, and then the next one moves. Catch up, move forward. Catch up, move forward. And by having that trailer that's piggybacking, that's one behind, it's going to give us our insertion point. So let's see how we do this. And we're going to write the partial code together, and then we're going to, I'm going to give it to you to finish off. So we're going to change a few things here. First, we're going to change current to call it front, because this is the pointer that we're using at the front of our traversal. So we're going to change all of these. And I could do a fancy editing thing to change it, but I'm not. So we're also changing, as you can see, get current and current value is going to also be front value. So now what we're going to do is we're making a new node. So we're going to need a new tree node. new node equals new tree node with a value of key. And now the second thing we're going to do is we also have to deal with like a base case, because if we want to have a pointer before our insertion point, that always works. But if the tree is null, if like you have a situation here where you have a tree where the root is just null, then there's no, there is no traversal. So we need a quick check. So basically, if root equals null, if the tree is empty, manually insert the new node as the root. So very simply, root equals new node, and we're going to return. We also want to make this void, because we're not actually searching, we're just inserting. So that's the first thing we're going to do, is handle that special base case of an empty tree. And yes, I am using the term base case like we usually do with recursion, even though this is not a recursive algorithm. So now the next thing we're going to do is we're going to have our tree node for front, and that's going to traverse down the tree. But we're going to have a second pointer, a second tree node, and that's going to I'm going to call that the trailer. And I'm not going to assign it up here. But let's go through the algorithm and see what we're going to do with this. So the first thing here is, while the front isn't at null, we're going to check and see, well, get our data. Is the data what we're looking for? Now, this is an interesting case. Let's say we're not inserting a 17. Let's say we're inserting a 20. So we're going to find the 20 where we're going to insert it, and we see that the 20 is already here. So what are we going to do? Well, the truth is we don't want to insert another 20 in our tree, because that's just going to make searching harder. So what really happens is, in a real binary search tree, when you do an insertion, if what you're looking for is already there, you'll either have a separate variable, like for example, in the node, like you might have, in addition to the data, you might have private int count, how many there are. I'm not going to leave this here, but just for now, how many of those data items are there? Oh, we have 120, we have 720s, we have 3020s. Or alternatively, and I'm not going to save that, alternatively, we might have an array in there, or an array list, or a linked list. So we'll have like a list of all the things that have the key 20 in there. So if this was an organizational chart for a company, you might have a key called vice president, and then you'll have like all the vice presidents, an array of all of them in there, or some other structure, maybe even another binary search tree. So anyway, if we're here, it means the key is already in the tree, so we can update this node in some way, and then return. And so that's what we're going to do here. We're not actually going to update it, but we would do whatever, because we don't know what we want to do. It's just a little test case. So we would do that, but since we only have the integer, we have nothing to do with that. But here's where the magic happens. So here, if the front value is less than the key, we've got to go to the right. So 10 is less than, let's say, the 17 we're looking for, so we have to go to the right. But before we do that, we say trailer equals front. Likewise, here, before we go to the left, we say trailer equals front. And let's see how that works. So if we're looking for the 17, we start with our front, which I'll just put as F, pointing to here, and our trailer, which we just have it as a T, pointing over nowhere. So we're about to do this line here, where we're moving to the right. But before we move to the right, we say now trailer points to what front points to, and then front points to its left. So see how this is piggybacking. Trailer caught up to front, and then front moved away. Now in the next iteration of the loop, 17 is less than 20, so we want to point it to the 15. But before we do that, we say trailer points to front, and then front will point to that 15. So again, now the trailer catches up to the front, and then the front moves to the next one. And now in the last one, the 17 is greater, so again, the trailer will point to where the front is, and then the front will point to the null, and then we exit the loop. And we don't need this null pointer exception. So at this point, after the loop, at this point, front points to null, but trailer points to the node that's before or above where the new node goes. So all you have to do here is add the code to finish the insertion. And that's what you're going to have to do here. So now you know if you're inserting a 17, you have trailer pointing here, you just have to put that 17 in somewhere. And so pause the video here and take the time to write a routine that is, or not write a routine, take this code, and this code is going to be under part 3 insert, and modify this code so that it finishes the insert. All right, and then we'll come back and then we'll talk about traversals. Okay, so let's take a look at that finishing off that insert routine, then see if yours matches what I'm going to have. So at this point, we know that front points to null, but trailer points to the one before. So all we have to do is decide, do we want to insert on the right or on the left? So if key is greater than front.getValue, well, that means we want to insert on the right. So we're just going to say front.getRight, not getRight, sorry, setRight, the new node. And let's get our parentheses right. And remember, new node is the node that we made way up here, that we haven't used in a while, but that has the new key in it. That has that key. Now, on the other hand, we want to insert on the left because it's less than the value in the node. So that's going to be front.setLeft, new node. And that's it. And so let's compile this. And we've got a little error in driver. And I made changes to driver, so let's fix that. And what I did to driver is, yeah, I accidentally took out a bracket, is I put a bunch of inserts in here. So let's first compile this. And run it, and it's not going to give us any output. But what I'd like you to do is now insert these values. So once you've got your insert routine written, insert those values, but also by hand do those inserts, like pretending you are the algorithm. And I'll pause the video, take a minute, and draw out the tree that it's going to come up with. All right, and so pause the video here, and then we'll do it together. All right, so let's do this. So we're going to first insert a 10, and that's our base case. So that's going to be our root. Then we're going to insert a 20. So 20, it makes a new node. 20 is bigger than the 10, so it's going to move front down to here on the right side. No, not. Yeah, but trailer is going to go over here. Let me make sure I put that right in the code before. And I did not. It's the trailer that we wanted to do this. And I'm surprised that didn't crash on me. Actually, I might be in the wrong directory here. And I will point out why in a second. Yes, I'm actually writing this in the wrong place. So I'm going to copy from part 3 star Java. Let's just copy over the vs.tree.java to here. Now, if I compile this, yeah, I'll get errors. And of course, it wouldn't work. I would have crashed. So I was working on the wrong code, and I noticed that this should be value. So now let's compile it. And we still have a get val. And I might still be working in the wrong directory. So let me just clean everything out here. Okay, looks like everything is cleared out. Let us go to part 4 traversal, driver.java, and that looks good. And part 4 traversal bstree.java. And let's look at that insert. So we're doing this, the root, it's fine. That's fine. All of that's fine. But here, value. And trailer is the one we're setting. So now let's try to compile it. Get value, get data. Is it get data? Yes, get data. Sorry, so I did it again. Did it again. Sorry about that. No. Oh, get trailer may not have been initialized. And that's because it doesn't know, because all of my trailer moving is in my my if statements. So it doesn't know I'm protected from that. So I'm just going to start that at null. Maybe even start it at root, you know. Get rid of that warning. And now we're running, if nothing else. Okay, so now we can come back to our algorithm. And what we've got here is we've inserted the 10 at our root. And now we're inserting the 20. So front is going to come to here, but trailer is going to be at the 10. And 20 is greater than the 10, so it's going to insert over here. Then we want to insert the 5. It's going to move front down to here. Trailer is going to be a 10, but it's going to insert on this side. Next, the 7. So it's going to start front at here, move front to here, move front to here. Trailer is going to point at the 5, but the if statement is going to insert the 7 there. The 8 is going to be here, to here, to here, and then the 8. And then the 3 is going to be here, and then the 3. And why don't we also insert a 25, and that 25 would go over to here. So that's our insert routine, and it should work. We could test it out by doing various, you know, like if we do a, let's try system out, print line, well, it's private, so we'd have to do it in a special routine, a debug routine. So actually, let's just jump into the next routine that we want to talk about here, which are traversals. And what traversals are is when you traverse a data structure, you go through every element in it. So if you have an array and you loop over every element in the array, that's a traversal. A linked list, that's a traversal. If you go to the first element, the next, the next, the next, all the way to the end. For a tree, a traversal is the same thing. You want to go through all of these elements in some order. And you might want to do this for a variety of reasons. One reason you might want to do this for is you might want to, you know, collect data. Give me all of the even numbers in this tree. Now that's not a search. Searching is looking for a specific number. If you want to find all the even ones, you're going to have to go at every item. It's like, oh, even, odd, 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 even, odd. And somehow or other accumulate that information. Or you might be, I want to double every element in the tree. So I want to make the 10, 20, the 5, 10, the 20, 40, the 3 becomes a 6, the 7 becomes a 14. So you want to go to every element and do something. Or you might just want to print every element. And we're going to focus on the print right now. So we're going to go back to our BST, and we're going to write a routine called traverse. And we'll do it up top here. And it'll basically, the idea, and we're going to make some modifications to this. We're not going to do this all at once. We're going to want to traverse the tree so we can print out every node. So let's think about linked lists for a second. If we had a linked list, if we had a list, or if we have an array, I mean, I'm not even going to write this for an array, but if we have an array, like if we had like int a 10 you know, fill the array with some stuff, and then we basically say for, you know, int I equals 0, I is less than 10, I plus plus, and then, you know, system out print line. Let's see if I have a, no, I don't have one, okay. System, I wondered if I had a shortcut. A sub I, and that's a traversal of an array. We just go down. With a linked list, we might have something like this. We might have, you know, node current equals front, you know, while node doesn't equal null, system out print line node dot get data, and then I'll fix this in a second. Current equals current dot get next. So this is how we might do this for a linked list. And so we have here, if we have a linked list and we have a few nodes, just 3 nodes, and if we have current, and current points here, and we can print out whatever's in that node, and then we do current equals current get next, we print out whatever's in that node, current equals current dot get next, etc. And that works, and it sounds like for a tree we're going to do something similar because we have those pointers, but the problem is we don't just have a get next, we have a left and a right. And there's another problem. Think about this for a second. If you don't see it immediately, pause the video and think, why can't we just do get left, get left, get left, or get right, get right, get right, where we can do just get next for the linked list. So pause the video for a second, and then after you've thought about it, start it up again. Okay, the reason is, as you probably figured out, you can't get back. Once we point over to here, once we're here, we can't get back to this guy over here. Now that's not a problem for a linked list, but for a tree, if we're at the 10 and we move to the left, we can't get back up to here to get to the 20. There's no way to do that. There's no previous pointer. Now there are tree structures that have pointers, that have all of these extra pointers going up and down, and you can do that, but usually you don't create those. Instead, you want to do something, you want to basically like, I want to do something with this 10, like maybe I want to print it out, and then I want to come to this 5, but I want to remember this 10, so that when I'm done with the 5, I can come back. And then when I'm at the 5, I want to go to the 3. And when I'm done with the 3, I want to come back. Think about that behavior. Where do we have stuff like that where we kind of go in a certain direction and then we come back? So again, if you don't see it automatically, pause the video, look back at the other algorithms that we've covered, think about them, and think about where did we have this behavior where we would do something here, we would then go forward in the process, but then we'd have a way to come back to where we left off and then go down another route. So what did it rhyme with? Yeah, I forget what we said in the slide in the Zoom the other day. But recursion. In recursion, we can do something here, and then by making a recursive call, go to the next level, and then come back. So we can say recursively, call left, but then when it's done, it'll come back to our current node. So what we're going to do is we're going to need a recursive call that gives us the node in the tree in question. So we're going to do this using a private function. So we got our public traverse, and basically what this is going to do is this is just going to call traverse with the root. So we're just using this to make that parameter. So now the root is going to be current, and basically we can think of our base case. If we're trying to, let's just say, print everything out with the tree, the simplest case, think about that for a second. Again, pause the video if you don't see it. But what's the absolute simplest tree to traverse and print out every node? Okay, so if you think about it, the easiest one is if it's null. Because if it's null, we don't do anything. Now, the next thing to think about is, well, if we're not in here, well, what do we want to do? Like, well, if it's not null, what can we do? Well, we might want to process the current node. And for us, that's going to be system out. We'll just do a print. Let's just do a print. Current.getData. And we'll just print it out with a comma after it. And what we'll do is down here when it's all done, we'll just do a system out print line to go to the next line, just to save some vertical space. So after we printed out the current node, we can recursively print out the left subtree with basically just calling traverse current.getLeft, and then recursively print out the right subtree. And that should do it. All right, so think this through, and now what you should do is you should not just type this in. What you should do is you should now run this on this tree, on the tree that we have over here, and actually run it through. So to start, we're going to call in here with root, current being the root, and it's going to print out 10. So the first thing it's going to print is 10, and then it's going to recursively call on the 5, and then trace it through, and you'll have to do some crossing out and things, but see what you get. So pause the video, and then we come back, then we will run it. And what you should do is once you have an answer, you should then run the algorithm and see what you get. All right, so welcome back, and we're going to go to the driver. And for the driver, we're going to now say traverse, or t.traverse. We'll recompile. Got a little error in here. That shouldn't be node. That should be tree node. Sorry about that. And not a star. And that's because I'm still in a C++ frame of mind. And now we see our results are 10, 5, 3, 7, 8, 20, and 25. Okay, whatever it is. But of course, we could have done other things there. We could have doubled every value. So processing the node could have been current.setData to be 2 times current.getData. You know, we could have done something like that. Or we could have only printed it if it was even, or all sorts of things. So, but we can also do a couple of other things with this. So let's try another experiment. Let's make a copy of this. And let's see what happens if we'll call this traverse 2. And we'll also make a third copy of this. And the third one will be traverse 3. And we got to change all of the calls, of course. Let's compile it. And I think did I rename the first one traverse 1? Or no, I got rid of the other traverse. So let's see what we have here. Sorry, we'll fix this all up. We've got that traverse, which then has public void traverse with no arguments. And that's just going to call traverse with the root. And then here we have traverse 2, and traverse 2, which calls traverse 2 with the root, traverse 3, which calls traverse 3 with the root. And what we're going to do is we're going to make a slight change. So the slight change for traverse 2 is, instead of processing the node up front, we are going to first recursively call on the left side, then recursively call on the right side, and only then will we process the node. And finally, in traverse 3, we'll do the other possibility. And the other possibility is first we're going to traverse on the left, then we're going to process in the middle, and then we're going to traverse on the right. So pause the video, and we know that the traversing where we process first and then traverse gives us this 10, 5, 3, 7, 8, 20, 25. See what you get just by changing that order. So pause the video, run through that, and then we'll take a look. All right, so welcome back, and let's see what we get. I probably should call the other ones, and I think I have to. Let's see, where are we? For traverse here, I forgot to put in the system out print line. And into the driver, we're going to have to call traverse 2 and traverse 3. And remember, traverse 2 does the processing at the end, and traverse 3 does the processing in the middle. And what do we see? We see that the first one and the second one are okay, it prints everything out, but the interesting one is the third one. The third one is printing out in numeric order. And this is another really cool feature of the binary search tree. All right, the cool feature about it is you can process the nodes in order, kind of like a sort. In fact, it kind of is a sort. And so we actually have special names for these traversals. The first traverse is called, a pre-order traversal. And we call it a pre-order traversal because you're processing you're processing in front. The second version, where we process at the end, we process after, and if you think about the logic here, it's pre-order is process and then call recursively. Process, then call recursively. So always printing out before we go. In the second one here, we're processing at the very end, so we call that a post-order traversal. So we're going to change that one's name here. And this one will be post order traversal. And the third one, where we're doing it in the middle, is the in order traversal. So, and the cool thing is an in order traversal of a binary search tree gives us a sorted list. It gives us the data in sorted order. So let's just finish this and we can talk more about it. Save it, go into here, and we'll just call these by their new names. Let's call pre-order traverse, post-order traverse, and in-order traverse. Got a couple of errors here. So let's go back into the code. In order traverse. And we get our same result. So there we have these traversals of these trees. So basically, we can insert, we can't delete yet. We don't have a deletion algorithm, and we'll do that. Give yourself a break. Take a break for 15 minutes or so, and we're going to do deletion. But then after we do deletion, we're going to talk a little bit about the runtime ramifications of this. All right, so give yourself a break now, and then we will talk about those things. Okay, so let's now talk about deleting a node from a tree. We can put a node into a tree, but and we can search for it, and we can traverse the tree, and we can do all sorts of things with it, but we still have to be able to delete. So let's think about deletion. Deletion is a little bit trickier than the other ones, and this one is we're not going to give you starter code for it. We're going to we will sub-goal label it, but we're not going to do all of it. But if you don't get it working, it's okay. To be quite honest with you, a lot of people in their data structures classes don't end up getting working. So, just make an honest effort to get through it. If you don't get it 100% working, attack it at some point in the future and get it going. You can also do a search online for final working code. Just do binary search tree deletion Java. Just because this is a summer session, it's compressed, and you don't like normally you do this. We would do this over the course of a couple of classes, but then you'd have like a week for the assignment to actually get all the code working, and we don't have that. We have the next day. So don't worry about it if you don't get this one working 100%. It's all cool. It's all normal. But let's look at this. So if we wanted to delete from this tree, unfortunately, there are a lot of cases. Like if you think about it, certain things are going to be really easy to delete. Like getting rid of this 8 down here would be easy to delete because all you have to do is point the 7 to the null. Deleting this 25 would be easy because to point the 20 down to null. So if you're doing a deletion, for delete, if you're trying to delete a leaf, it's easy, a leaf, it's easy. Deleting a leaf, and again, I really wish I had a better eraser. This is an awesome pencil. This is the best pencil ever. It's the Palomino Blackwing 602, but the eraser, not so good. If we're deleting a leaf, it's really, really easy. All we have to do is point its parent to null. That's easy. You want to delete the 25, point the 20s to null. And if you think about that, if you're pointing the 20 to null, you're doing something kind of similar to the insert in that if you're deleting the 25, you have to have a pointer to the 20. And that's that piggybacking again. But that's pretty easy to do. So deleting that situation is pretty easy. So let's think of the next type of node that's to delete. Well, pause for a minute and then think of what else would be a little bit harder but still doable. Well, that would be something like the 20. If you want to delete the 20, you're going to have the 10 pointer point to the 25. Or if you want to delete the 7, the 5 pointer has to point to the 8. So those are situations, the 20 or the 7, those are situations where you're deleting a node with one child. Well, if you're deleting a node with one child, all you have to do there is point parent to deleted node's child. So if you want to delete the 20, you point this over to here. You want to delete the 7, you point this over to here. So it's conceptually pretty easy. It's just, it gets a little bit messy in terms of if statements. You got to be like, if the left one is no versus the right one, etc. But the last situation, and again, well, you can just back up the film if you want to see that. The last situation is something like this. Actually, I'm going to grab another piece of paper. So we have the 10, the 5, the 3, the 7, the 8, the 20, and the 25. So the last situation, the most complex situation, is this one. What if we want to delete a node with 2 children? That's tricky because you can't just point the 10 to, you pointed to the 3, you lose these. You pointed to the 7, you lose these. It becomes a little bit of a mess. So you have to think about what you have to do here. Well, if we get rid of this 5, we've got this hole in the tree, and we got to fill the hole. We want to put something in the hole that's going to fulfill binary search tree property. And the easiest way to do that is we need a node such that everything on its left is going to be smaller and everything on its right is going to be bigger. So what we have to do, and let's even add another couple of nodes. Let's add another node here. Let's pretend there was a 4 there. So what we have to do is we have to find a node that we can move into here easily. And that's easy to find. We can either look for the smallest node on the right subtree or the biggest node on the left subtree. And so the biggest node on the left subtree is the 4, so we can literally just take this 4 off and put it over into here. And if you think about this, it's kind of like deleting this 4 and moving it up here, and this is always going to be a leaf. Or even if it's not a leaf, it's going to be a node with at most one child on the other side. So the other deletion operations are already going to work. So that's kind of an outline of the deletion algorithm. And so let's sub-goal label it, and then you should spend some time trying to get this to work. But in fact, actually what we should probably do, and yes, let's do that, is let's sub-goal label it. Then continue to watch the next segment of the video, which is going to talk about runtime analysis, but then spend time to see if you can get the deletion working. But don't stress if you have problems with it. So let's sub-goal label. So, and actually, we're going to pause for a second. I'm going to save this, and we're going to pause so I can copy this into another folder, so each folder has set materials in it. Okay, so now we're going to look at the delete routine. We're just going to look at the sub-goals. And so to start with the sub-goals, I copied over the search routine because what we have to do is find the node that we want to delete and the node above it. So we want to get, if we want to delete this older 5, we want to have a pointer above it so we can, have that for moving pointers around, and we need the pointer to this node that we found. And the same for any other deletion. And that was just a comment. That was just a comment from the old from the insert routine. So we're actually going to move this comment down to here. And here it's just, if the tree is empty, nothing to delete. So now we start with our front and our trailer. And once again here, the little bit of a difference here is if the front value equals the key, we found the node we want to delete. So while front value is equal to no, and instead we're not going to use front value, we're going to say if front doesn't equal no and front.get data doesn't equal to the key, because we want to stop if we find the key. So this actually changes a little bit, that we do want to piggyback, and if not front value, but if front.getData is less than the key, we want to search to the right. And on the other hand, if it's greater than the key, because we know it won't be equal because we're testing that in the while loop, move to the left. So it's a little bit different here. This is going to do the piggyback loop until we either find the node or null if the node is, or if the key isn't present. So at the end here, we basically have one of two situations. Either front points to null if the key isn't present, or rather, why don't we just say if front equals null, see if, well, rather, if the key wasn't in the tree. So if the key wasn't in the tree, we just return. There's nothing to delete. But if we get here, that means that front points to the node we want to delete, and trailer points to the one above it. So now we have our three situations. Case one, the node we want to delete is a leaf. Well, we got to determine that, so that's going to be if front.getLeft equals null and front.getRight equals null. And let's just do that. So if both of those, then we know that the node in question is a leaf, so we basically have to repoint front's parent to null. Once we've done that, we have case two, which is else if, and so here you'll need check to see if front has one child, because if it's not, that's our second case. That's the case where we wanted to delete the 20, where it has one child. And then if that's the case, repoint front's parent to front's child, whatever child is left. And of course you'll want to draw out your diagrams. And the final situation is here. If we get here, then front has two children. So what we want to do, two children, so what we want to do here is find the node with the smallest, let's go with this way, the largest value on front's left subtree and replace front with it. And as a little hint, I'll tell you that if you want to find the largest value on the left subtree, you just go left once and as far right as you can. And the second hint that I'm going to give you is when you want to get rid of that node that you're, like here, if you're moving this 4 in, you're basically kind of doing a semi-recursive delete, and this will only have 0 or 1 children, but that's a little bit of a hint. But that's the routine, and I'm going to compile this. It won't run, but I want to make sure there are no syntax errors, and there is a syntax error. So I want to get rid of that, even though it's just a I guess the syntax error there is that there's no Boolean at all. So if I just put true in here, yeah, it compiles. Because you have to replace that with the actual Boolean in there, but I'll leave that in there so you can compile it without any issues. But you have to handle each of these cases, and that's going to be our deletion. Okay, so take another little break to think this through. I would trace through a couple of examples, but don't code this yet. All right, trace through a couple of examples, make a binary search tree. You can just like write one up. You can be like, 10, 5, 20, 50, 35, 7, 6, just like make something up, and then just go through the deletions to work this through, and then still don't code it. Take a break. Come back here and continue watching here, because we're going to continue to talk about runtime a little bit, and then finally work on writing this. Okay, so take that little break. Go through a few, take the break, and then come on back. Okay, so let's talk about runtime a little bit. So we already see there's a partial ordering to this. And in a binary search tree, so like if you have a binary search tree and we've got a 10, or let's make it, a 70, 20, 10, 30, 100, 120, 80, 90, etc. It's got this tree structure, and it kind of does look kind of binary searchy. And the truth is, the perfect binary tree, the perfect binary search tree or binary tree, is going to be full and balanced. It's going to be like this, and it's going to look a lot like the merge sort tree or a binary search tree, and you're going to have, in this full and balanced situation, you're going to have that same situation where you have log n, and LG is for log base 2, levels of your tree. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and we have 0, 1, 2, 3, 4. 2 to the 4 is 16. So there's a -1 in there, but it gives you that logarithmic level. So that means if your tree is full and balanced like this, you're going to get, your search is going to be throw away half, throw away half, throw away half, and so your search is going to be log n, or specifically order log n if the tree is balanced, full, complete, any of those words. If you think about the insert is the same thing. Insert is, we got to find out where to insert, so it's going to go down the tree for that. So insert is going to also give you that logarithmic performance if the tree is full and balanced. Delete's the same thing, because to delete you have to find the node, and then it's just a little ticky-tack stuff. So all of these are log n, and then the traversal, if you think about the traversal, when we do the traversal, when we do the traversal, we just hit every node once. We never repeat ourselves. So since we only hit every node once, our traversal is linear. that means that if we have a binary search tree, we can get it in sorted order in linear time. Now, of course, it doesn't mean that's not a linear sort, because think about this. If we build a binary search tree, if we add n items to the tree, we've got to insert, 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 and each insert is going to be log n. So the idea of, add n items to the tree is going to be log n for each item, but we're going to do n of them. So adding n items to the tree is n log n. So using a binary search tree sounds like it could be an n log n way of sorting and then maintaining. So it's kind of like sort the list n log n and then binary search. And it is kind of analogous to that, except without the cost of having to shift in the array. The problem is, what happens if you have something like this? What happens if you go to, let's go to our driver, go to the right window here. What if we insert, we don't insert here. What if we insert, and I'm not going to save this version. Etc. Well, if we do that, we're going to get, the root's going to go here, then 2, then 3, then 4. If we insert into a binary search tree in order, we're going to get a degenerate case. We're going to get a linked list because we're just going to have like right. In which case, all of those nice logarithms are going to become linears. So this is the problem. Let's go back to the test case. This is the problem with the binary search tree. The binary search tree gives you this ability to get n log n for overall and n log, linear, n log n to insert n items, linear traversal, which can give you the sorted data, logarithmic operations for insert and deletion. The problem is it relies on the shape of the tree. So what is one to do? Well, one thing you can do is when you're building it from a data set, you can grab items from the data set in random order to try to encourage its starting. Because, if it doesn't look exactly balanced, like if we come back up to here, it's not perfect, but it's pretty good. So it'll get close to that type of performance. Or maybe you rebalance the tree periodically. The truth is, you're probably not going to use a binary search tree. The truth is, you're probably going to use a more advanced structure. Like the built-in Java linked list is not a singly linked list. The built-in Java linked list is a doubly linked list. But we study the singly linked list because that's our building block. There are types of data structures, and let's go just to a desktop share. There are types of data structures, and I'm bringing up a web browser here. So like, for example, a B tree. Well, let's not even jump to a B tree. There's a 2-3 tree, and a 2-3 tree you'd study in an algorithms class. And a 2-3 tree is a type of tree. It's like it's a full and balanced tree, but unlike a binary search tree, which only has up to 2 children, a 2-3 tree, every node has either 2 children or 3 children. Or there's something called a red-black tree. And a red-black tree, has a different tree structure, but they're kind of like, you start with the binary search tree and it's the next level up. Or another one that gives you a variation is something called a splay tree. And a splay tree doesn't truly give you guaranteed performance, but it exploits the most recently used idea that, if you search for something in a tree now, you're probably going to search for it again, so it leaves it near the root. And here I brought up this B tree. Like a B tree is a further extension. A B tree is a tree where like every node has like 511 or 512 children, and it's kind of built off of a 2-3 tree conceptually, which is built off of a binary search tree conceptually, and that's one of the ways that major databases are stored in. So there's this is just the starting building block. So basically here, that's most of what we wanted to say about binary search trees, and we'll talk about other trees and stuff as well. But give yourself some time now that we've talked about the runtime a little bit to see about implementing that delete routine. Again, don't stress if you don't get it 100% working. Yeah, and that's it for binary search trees.